The universe is built from elements. These fundamental building blocks of matter have captivated humanity for centuries. From the ancient alchemists seeking to transmute lead into gold to modern chemists exploring the frontiers of material science, the quest to understand and control elements has been a driving force in scientific inquiry. Early civilizations possessed a rudimentary knowledge of elements, identifying substances like gold and silver that occur naturally in their pure forms. These shiny, malleable materials quickly found their way into jewelry, currency, and art. Yet the true nature of elements remained shrouded in mystery for millennia. The emergence of alchemy, a blend of philosophy, mysticism, and proto-science, marked an important step in the exploration of elements. Alchemists, driven by a desire to understand the essence of matter and unlock its hidden potential, developed techniques for manipulating and transforming substances. Though their ultimate goals, such as the creation of the elusive philosopher's stone, proved unattainable, their experiments and observations laid the groundwork for the scientific revolution and the birth of modern chemistry. As the study of chemistry evolved, so too did the desire to organize the growing list of known elements. Early pioneers in the field recognized that elements exhibited patterns and relationships, hinting at an underlying order waiting to be deciphered.
One of the first attempts at classification came from the French chemist Antoine Laurent de Lavoisier in the late 18th century. Lavoisier, often hailed as the father of modern chemistry, meticulously categorized elements based on their properties, dividing them into 4 groups: gases, nonmetals, metals, and earths. This rudimentary system, though a far cry from the elegant structure of the modern periodic table, represented a crucial step towards imposing order on the seemingly chaotic world of elements.
Building upon Lavoisier's foundation, German chemist Johann Wolfgang Dobereiner, in the early 19th century, observed intriguing patterns in the properties of certain groups of 3 elements, which he termed triads. Dobereiner noted that the atomic weight of the middle element in each triad was approximately the average of the other 2. For example, in the triad consisting of lithium, sodium, and potassium, the atomic weight of sodium fell neatly between those of lithium and potassium. This discovery, while limited in scope, further fueled the belief that a more comprehensive system of classification was within reach. The mid-19th century witnessed a pivotal breakthrough in the quest to organize the elements. Russian chemist Dmitry Mendeleev, working independently of his contemporaries, formulated the periodic law and created the first widely accepted periodic table of elements. This groundbreaking achievement would revolutionize the field of chemistry and solidify Mendeleev's place among the giants of scientific thought.
Mendeleev's periodic law stated that the properties of elements are a periodic function of their atomic weights. Armed with this insight, he arranged the known elements in order of increasing atomic weight, noticing a recurring pattern in their chemical and physical properties. This led him to construct a table with rows and columns where elements with similar properties were grouped together.
The true genius of Mendeleev's table lay not only in its organization of known elements, but also in its predictive power. He boldly left gaps in his table for elements yet to be discovered, confidently predicting their properties based on their position within the periodic structure. The subsequent discoveries of gallium, germanium, and scandium, each precisely matching Mendeleev's predictions, cemented the periodic table's status as a cornerstone of modern chemistry. While Mendeleev's periodic table represented a monumental leap forward, it was not without its inconsistencies. Certain elements seemed out of place based solely on their atomic weights. The early 20th century brought a deeper understanding of the atom's structure, thanks to the work of physicists like Ernest Rutherford and Niels Bohr. This new knowledge paved the way for a refinement of the periodic table, courtesy of English physicist Henry Moseley.
Moseley's groundbreaking experiments in X-ray spectroscopy revealed a fundamental property of elements, the atomic number. He demonstrated that each element possesses a unique positive charge within its nucleus, which he termed the atomic number. This number, representing the number of protons in an atom's nucleus, provided a more fundamental basis for organizing the elements than the previously used atomic weight.
The adoption of atomic number as the organizing principle for the periodic table resolved the inconsistencies that had plagued Mendeleev's version. Elements were now arranged in order of increasing atomic number, resulting in a more accurate and elegant representation of the relationships between them. Moseley's discovery marked a turning point in our understanding of the periodic table, transforming it from a remarkable empirical tool into a framework deeply rooted in the fundamental nature of atoms. Section 5. The Modern Periodic Table, a Symphony of Structure and Organization. The modern periodic table stands as a testament to centuries of scientific inquiry. This iconic symbol encapsulates a wealth of information about the elements and their properties. The table's structure, with its rows, columns, and distinct regions, reflects the underlying order of the elements, a symphony of structure and organization. Section 6. Unveiling the Secrets of Periodicity, Trends, and Patterns. The periodic table reveals trends in element properties. Atomic radius decreases across a period and increases down a group. This is due to increasing nuclear charge and added energy levels. Ionization energy increases across a period and decreases down a group. This pattern is due to nuclear charge and atomic radius changes. Section 7. The predictive power of the periodic table. The periodic table's predictive power extends far beyond simply organizing the elements and highlighting trends in their properties. It serves as a roadmap for chemists, guiding their understanding of chemical reactions, predicting the formation and behavior of compounds, and even driving the discovery of new materials. For instance, the periodic table allows chemists to predict the types of bonds that will form between elements based on their positions. Elements on the left side of the table, with their low ionization energies, readily lose electrons to form positive ions, while elements on the right side, with their high electron affinities, tend to gain electrons to form negative ions. This fundamental understanding of ionic bonding allows chemists to predict the formation and properties of a vast array of ionic compounds. Moreover, the periodic table provides insights into the reactivity of elements. Elements in the same group often exhibit similar reactivity patterns. For example, the alkali metals in Group 1 are all highly reactive metals that readily react with water to form alkaline solutions. This predictability allows chemists to anticipate the behavior of elements and design experiments accordingly. Section 8. The Ever-Evolving Periodic Table, a testament to scientific progress.
The periodic table, though a cornerstone of modern chemistry, is not a static artifact. It is a testament to the ever-evolving nature of scientific understanding, constantly being refined and expanded as new discoveries come to light. Since Mendeleev's time, scientists have discovered and synthesized numerous elements beyond those initially known.
The ongoing synthesis of new elements, pushing the boundaries of the periodic table, exemplifies the dynamic nature of scientific inquiry.
These new additions, often created through high-energy collisions and particle accelerators, expand our understanding of the fundamental building blocks of matter and challenge the limits of the periodic table.
The discovery of new elements often necessitates adjustments to the periodic table, refining our understanding of its structure and the properties of elements.
These adjustments highlight the iterative nature of scientific progress, where new findings constantly challenge existing models, leading to a more complete and accurate understanding of the universe around us.
The periodic table, in its ever-evolving state, embodies this spirit of scientific exploration, reminding us that the quest for knowledge is an ongoing journey with no finish line.